Okay, so now for the second half, we're going to go through some of the practice problems related to these. So the first one is one that's pretty similar to the last question that we had on the end of the basic slides. In this case, though, right, the frequency is staying the same, and the intensity is increasing. So we're making the opposite change, so it has right the opposite effect, right? By not changing the frequency, we keep the energy the same, which means the energy given to each electron is the same. So the kinetic energy and therefore the speed has to be the same. But the intensity going up means that we have more photons, so we get more electrons, right? More interactions. Okay. So now some calculation ones. So this statement, right? This word threshold is very important, right? That's sort of like the minimum amount of energy necessary for the photoelectric effect to happen at all. And so we care about it for sodium and aluminum, so two separate problems. And when I see the word threshold, that basically means that there is no energy left over as kinetic energy. In other words, whatever energy I put in as light is all used up to sort of escape the metal, right? Or, right, using the equation, K max HF minus phi, right? Whenever you see the word threshold, this is really 0 equals HF minus phi, or HF equals phi, right? That's the core when you see that word threshold. So we need to look up in the table, if this was an AP problem, you'd be given them, right? The work functions for sodium and aluminum, which is done right here, right? And then we just plug it in and solve for frequency. Once we get frequency, we can relate frequency and wavelength using C is F times lambda, right? That relationship doesn't change. And so this is kind of them doing that work, right? They calculate the threshold frequency from the work function, then they calculate the wavelength from the frequency, right? Notice that the sodium work function is actually in the visible light range, right? That would be something that if you shone actual visible light, in this case they say it's blue and violet, maybe a little bit of green, but they say no, you would see the photoelectric effect happen. Aluminum, however, right, more of an everyday metal, you would not without ultraviolet light. So that's why you don't see that in everyday situations. Okay, so next one. We have light, we have information about the light, and we have information about the work function, and we want to know the maximum kinetic energy. Well, this is the same exact relationship, right? K max equals HF minus phi, right? That's the one that's going to tie all these pieces together. And really, right, remember, HF is an energy. And so all it is just that value, 2.7 electron volts. And the work function is an energy, which we have right there. So we just plug the numbers in. It's just 2.7 minus 2.3, which is, right, 0.4 electron volts. Sure enough. Yep. So this next one is just a very similar idea, but just a couple more steps. Right, here we want speed, not kinetic energy, and we also want to find the stopping potential. We know it's sodium, and we know the wavelength of the light, right? So that means, right, when I see the word sodium, that means look up the work function, right? If I know the work function of sodium and the energy associated with light of that wavelength, then I can find the kinetic energy left over. And if I know the kinetic energy left over, I can find the speed, right? So let's kind of put those pieces together, right? K max equals HF minus phi. Well, kinetic energy is just 1/2 m. And since this is an electron, it's the mass of an electron, we don't know the frequency, but we do know the wavelength. So using C equals lambda times F, we can rearrange that to find that the frequency is C over lambda. That's actually really sloppy, so let's rewrite that a little nicer there, right? And so this right here is really the only equation we need for the first part, right? I've put all the pieces together, right? We know the mass of the electron, we know H, we know C. Those are all constants that are on the AP sheet. Lambda and phi are given in the problem, right? So you just plug it in and solve. And so the next slides will be them doing that. right? So they do it in a couple different steps, but it's the same idea, right? They found the energy associated with the photon. They took away the work function's energy to figure out the maximum kinetic energy. Notice this important step here, right? They have to convert it to joules. If you want a velocity in meters per second, your kinetic energy has to be in joules. If I only ask about energy, it doesn't really matter. You can leave it electron volts or joules, but if I want a speed, you've got to work with joules, SI units only. So this is that last step. You see, right, it's quite fast, which makes sense. They're electrons. So now, right, there's another relationship then that we need, which is this is another energy conservation thing, right? This is really U electric equals K max, right? We're converting all the kinetic energy into potential, and the potential electric energy is E times the voltage. And so that's just this rearranged. And sure enough, if you calculate that out, you get 1.39 volts. Okay. Really, the key is that energy conservation is really the core of this. The only thing that's different is we're introducing the idea of a photon energy into our energy conservation calculations. Okay, so now some graphical ones, and these are really important, right? The AP test really likes graphs, and so you have to be able to sort of recognize these. So first thing I read, right? I'm changing intensity. I'm not changing frequency at all. So if I don't change the frequency, right, that means that every electron that travels out gets the same amount of energy, no matter what, in sort of the before and after pictures. And that means it takes the same amount of energy to stop. So this, right, is showing the position of V stop. That can't change, right? Every electron has the same energy just like it did before, so that can't change. That eliminates B and C, right? But by reducing the intensity, we've reduced the number of photons. And since each photon gives its energy to exactly one electron, by reducing the number of photons, we've also reduced the number of electrons. And less electrons means less current. So I naught has to go down. And sure enough, right here it does. So it should be A. Right? Good. Okay, so now we're changing something else. We are increasing the work function. So the first thing to note is that by increasing the work function, we've made it harder for electrons to get out, right? If the light gives it a certain amount of energy and the work function takes some of that energy away, now there's less energy available to the light. There's less, or to electrons. There's less kinetic energy for the electrons themselves. If the electrons have less kinetic energy, that means that they're easier to stop. So in this case, V stop must go down, right, or become less negative. So that eliminates A. However, because we didn't change the intensity of the light, if we were able to get all the electrons, we should see the same total current, right? So that eliminates C. So B is the same current with a lesser stopping potential, and that should be the right answer. Right? Okay, so now we've changed our graph a little bit, right? This is the current as a function of the wavelength, right? We are changing the wavelength. Sorry, we're looking at the sort of the effect of wavelength after a change in the work function. So once again, we're changing the work function. So this explanation is the exact same, right? Increasing the work function means that we have less energy left over. That means if we want a current to happen, exactly the same, the light's energy has to go up. So that way HF minus phi is constant, right? If this goes up, that has to go up. So if we want HF to go up, that means frequency has to go up. But frequency and wavelength are inversely related using C equals lambda times F. So if we want the frequency to be higher, the wavelength has to be smaller, and a smaller wavelength means it moves that way. And that is what we see in option C, right? What this is really showing is that if the work function goes up, it takes more energy from the light to make the current happen, which makes sense. Like it's more expensive to leave. And more energy means a shorter wavelength. All right, so back to this stopping potential one. So now here, right, the work function is bigger than the photon energy. right? Mathematically, that's saying HF minus phi is less than 0. So what does that tell us about the energy left in the electrons? Well, there can't be any kinetic energy. If there's no kinetic energy, there's no current, and that's C. Right? We didn't give any of the electrons enough energy to actually escape the metal. Those ones are really important, so make sure that you go kind of slowly through those and make sure they make sense. So now another more conceptual one, right? We're asking about the energy and we're given the color, right? That's a frequency statement, right? Red light is a lower frequency than blue light. So because E equals HF, the frequency being lower for red means that the energy is lower for red. So it should be C. Okay. Oops. So now we are looking at the change in intensity without changing the wavelength and sort of trying to describe what happens. So not officially a calculation, but description, right? Intensity is reduced, not changing the wavelength. So these first two statements are sort of illogical, right? Photons are packets of energy, but they're not packets of matter. So size doesn't even come into it. This is a nonsensical statement. So it can't be A. Travel slower. Well, the speed of light is still the speed of light. Even though we're not following the wave model, we're not changing the rules about what light does. Light travels at the speed of light, so this can't be possible. Less energy is a statement about frequency or wavelength, but we didn't change the wavelength. So while this could be true, right, that's something that can exist, it's not correct in this description. However, intensity, that's a count, a number, right? If you see things like fewer or more or twice as many or stuff like that, you should be thinking intensity. Intensity is a count in this quantum mechanical model. So a lesser intensity means a lesser count, fewer photons, that's right. So it should be D. Okay, so here we are doubling the frequency, right? That's the only thing we're changing. We know that the frequency was already enough before to have the photoelectric effect occur. So kinetic energy doubles, right? Kinetic energy, we know how to relate that to it, right? So let's look at that equation, see if we can reason it out. So we take this and we double that. This is the same. So if we do that, hopefully you can see without any more math. If you're not convinced, pick some numbers and test it. But that's not going to double. It will increase the kinetic energy, but it won't double, right? Because the work function doesn't change. So it does increase, but it doesn't double. The speed, therefore, is going to follow the same rule. It's not going to double either. It will increase, but it will not double. The next two, notice they're about numbers, right? The number, twice as many. Those are statements about intensities, which we didn't change. So those are out, right? This is about intensity. That means that all of them are wrong, so it's got to be E, right? Those two are intensity statements. Okay, so we have a wavelength that does not get the photoelectric effect to happen, and we want to make it happen. That means we need light that has more energy, right? So we need more energy. That's what that is telling us. So these two, right, intensity, that doesn't affect the energy. Those are out. Those will not change the energy. Between A and B, right, we need E equals HF to go up, which means we need a higher frequency. But a higher frequency, because of the relationship between speed, frequency, and wavelength, means that a higher frequency corresponds to a shorter wavelength, so it should be B. Okay, so moving on to this next one. Again, identify what's happening, right? The intensity is increased. And want to know how it affects the stopping potential. once again, we're relating, it's a question about two things that are unrelated, right? This is number of photons, and this is sort of energy. Those things are not related in the quantum mechanical model, so we would expect no change, right? More photons doesn't mean that there's more energy sort of per electron. It just means that there's more electrons that can get excited. They're still equally easy individually to stop. And so sure enough, it's unchanged. Okay, so here's a calculation one. So we want the longest wavelength, which means, this means lowest energy. So in this context, right, the lowest energy is saying that we need enough energy to get the electrons off the surface, but nothing left over, which means K max equals 0, right? There's nothing left over. It's the bare minimum. And so this must equal HF minus phi. But we know the relationship between frequency and wavelength, which comes up a lot. That one's actually kind of worth remembering. And so this is the equation we really have to solve, right? We have all the pieces to do that, right? There's the work functions; those are just constants. Solve for the wavelength, right? And if you do that, rearranging first, you'll get lambda is hc over phi, and then you plug in your values. You should probably use the value for h that has the electron volt unit, right? Both of them on the AP sheet, because we have units of electron volts. It makes your life a little bit easier. So if you do that and plug everything in, you should get 4.97 times 10 to the negative 7th meters. Notice that if you always work in SI units, you always get SI units out, which is meters. And so then you can leave it like that, or recognize that that is 497 nanometers. Right? This is the sort of reasoning bit, right? That's what lowest energy means, or longest wavelength means. Okay, so for this one, I found it actually easier to do part B first, right? The statement that we're given, right, this just barely, that's again telling us that K max equals 0 for that frequency, right? And so we can use that very quickly to find the work function, right? If K max equals 0 for that frequency, then we have HF equals phi, just like we did before, but now we're solving for the work function, right? And we know H and F. And also, one thing important to note, there is a typo in this, right? This right here is the plus 14th power, not negative, right? A frequency of 10 to the negative 14th hertz is kind of illogical. So we can solve for phi just by plugging H and F in. And so if you do that, you get phi is 4.8 times 10 to the negative 19th joules, and that is 3 electron volts. Right, the conversion between joules and electron volts is on the AP sheet. It's just divided by 1.6 times 10 to the negative 19th. So that answers part B. And with part B answered, now part A is pretty straightforward. Right? We want to know the stopping potential, right? So we have a couple different relationships for that. So first, right, now K max is not 0, right? We have a higher frequency. We have some leftover energy. But it's still true like that, right? That energy relationship. But we know how to relate the maximum kinetic energy to the stopping potential as well, right? It is, right, all converted to electric potential. So therefore, those two things are equal, right? We can rearrange and solve. We're going to get V stop equals HF minus phi over the charge of an electron. And once again, now we know all those numbers, right? We have the frequency from the problem. We've just found phi in part B. H and E are constants on the AP sheet. And so if you plug that in, you get 0.625 volts. Okay? There are lots of problems that can come out of this. This is probably the most important part of the quantum mechanics section. You notice how there's calculations, there's conceptual questions, and there's graphs. There's lots of sort of, if you change this, what happens questions. You have to be familiar with all of this. And so it's really important to make sure to go through these and that you understand them.